Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Identify the hybridization and carbon type for each CH bond. Bond X, the carbon-bearing H, kiss smiley, is a secondary sp3 carbon. It has an ethyl group on one side and a CH2 group on the other, plus 2 H atoms. This is a secondary, 2 degrees, aliphatic CH bond. Bond Y, the carbon-bearing H, Y, is also a secondary sp3 carbon, CH2 group flanked by the X carbon and the vinylic carbon. This is also a 2 degrees aliphatic CH bond, but it is allylic because it is adjacent to the C is equal to C double bond. Allylic CH bonds have lower BD because the resulting radical is stabilized by resonance with the double bond. Bond Z, the carbon-bearing H, Z, is an sp2 vinylic carbon, part of the C is equal to C double bond. Vinylic CH bonds have the highest BD among these because the resulting vinylic radical is in an sp2 orbital, which has higher s character than sp3, making it less stable, higher energy radical, thus requiring more energy to break. Moving on to the next step. Rank BD based on radical stability. Lower radical stability is equal to higher BD. Vinylic radical, from Z least stable radical, sp2 carbon, no resonance stabilization, highest BD. Secondary aliphatic radical, from kiss smiley, moderate stability, intermediate BD. Allylic secondary radical, from Y most stable radical, resonance stabilized, lowest BD. Moving on to the next step. ZXY. And for the final step. A. YXZ, incorrect. This would imply allylic CH has the highest BD, which contradicts the stabilization of the allylic radical. C. ZYX, incorrect. This would place allylic CH, Y, above secondary CH, kiss smiley, but allylic radicals are more stable than secondary radicals, so BD of Y BD of X, T, YZX, incorrect. Placing allylic above vinylic contradicts the high BD of vinylic bonds. Therefore, the correct answer is B. Therefore, the correct answer is option B.